We've been talking about conjugated unsaturated systems, and we remember that when we talk about conjugated systems, we're talking about at least 1, 2, 3 p orbitals in a line gives us a conjugated system. So here we have 1, 2, 3, 4 p orbitals all in a line, okay? So that typically for conjugated systems, the electrons in these can communicate with each other. Now here we see we have, this is a conjugated system. We have an sp3 hybridized carbon here. So this is an isolated pi bond. It can't communicate with the pi bonds over here through resonance types of things. Okay, so I'm just going to zoom through these slides that we already took a look at. We talked about the heat of hydrogenation and how we can see that conjugated systems are more stable than we might otherwise expect. I should have taken. Okay, we talked about the allylic system, and we're going to talk a little bit more about it today. We talked about this reaction and the fact that we get this distribution of products, whether we start from here or we start from here, and perhaps that can be explained through this resonance structure. Now, one of the things I want to mention about resonance, remember this arrow is indicating that the real structure is somewhere in between these two. It's not this per se, and it's not this. These contribute to the real structure, and the real structure actually has the positive charge delocalized here. It's delocalized most on these two carbons, but we sometimes will draw it with a dash line indicating that the real structure has the charge delocalized. And we can indicate that with resonance by saying this contributes, that's not the true structure. This contributes, it's not the true structure. The real structure is adding those two together. And in fact, resonance was one of the concepts that people are having some difficulties with. We're going to talk about carbocation stability a little bit more. Okay, so resonance is a valence bond description of electron delocalization. We're going to talk about that right now. And right now we're just going to go through some rules of resonance because this is an area where you folks need to think about things a little bit more. And the thing we want to remember mostly is this is not a reaction. This is showing that the true structure is a blend of these two structures. Down here, the true structure of this is a blend of these three structures. This is a radical, this is a cation. When we move 2 electrons with our curly arrows, we use a double-sided arrow. When we move 1 electron, we use single-headed arrows. They only have, they're fish hooks. So here's our resonance theory revisited. Don't bother reading this. This is all of them. We're going to go through each of these. This is just kind of some of the rules of resonance. So one of the things we have to remember is that resonance structures exist only on paper. That's not true. They exist on chalkboards too. But they're a human construct. We just use them to explain a phenomena. And it's this phenomena of electron delocalization that we're explaining with resonance. So they have no real existence on their own, but they're useful because they allow us to describe molecules, radicals, and ions for which a single Lewis structure is inadequate. That's it. Remember that they're not real, but they're helping us describe this delocalization of electrons. And we say that the hybrid of all of them represents the real molecule. Now what we're going to find out now is that some resonance structures may contribute more to the true structure than others. So we're familiar with this. These are resonance structures, and this is resonance. We can indicate we're going from one structure to the next with our curly arrows, and we're just saying because these p orbitals are all in a line and in the same plane, we can think about moving the electrons from this double bond over to here, because that's an empty p orbital if this structure were just static. And then we end up with this. So our charge, now we have an empty p orbital over here and 2 electrons in this p orbital. In reality, those 2 electrons are going, we have 2 electrons that are in 3 atoms in the pi system rather than 2 electrons and just 2 atoms here and an empty p orbital there. So this is resonance. This is not resonance, okay? So we can push our curly arrows. However, notice, and this is where we want to remember, there's actually a lot more hydrogens on this thing, right? There's 3 hydrogens here, there's 1 hydrogen here, there's a hydrogen here, and there's 2 hydrogens here. We have to remember that because we don't draw it out all the time. If you're having difficulties, I would suggest that for a while you draw out the hydrogens specifically if you're finding you're missing those and when you're doing reactions. So in this particular, this is actually a chemical reaction because we're moving a proton from this carbon to this carbon. So it's not a resonance structure. This is actually a chemical reaction. It's a 1-2 proton shift. Okay? So only electrons move. Atoms don't move when we draw different resonance structures. If an atom moves in the next structure, that's a chemical reaction. It's not a resonance structure. We must have valid Lewis structures. So we can envision pushing our curly arrows to go from that thing to this, but this thing has 10 electrons around this carbon, okay? We have 5 bonds to carbon. I saw a few 5-bonded carbons on the midterms as well, and you'll notice I'll draw an arrow and say you have 5 bonds to this carbon. We never have 5 bonds to carbon. So they have to be valid Lewis structures. All structures must have the same number of unpaired electrons, and this comes into play mostly when we have radicals. So here we're trying to indicate resonance. This is not valid. This is not a valid resonance structure because we're indicating that there's different spin. Okay, here we would talk about this thing having a spin of 1/2 because it has an odd number of electrons in the system. Remember, electrons can have plus half spin or minus half spin, and we have 3 electrons in this pi system because we have 2 in this pi bond and then we have 1 in this p orbital. We have 3 in the system, but we have to conserve our spin. So we wouldn't draw this as a valid resonance structure because that's indicating that we actually have a spin of 3/2 instead of a spin of 1/2. And don't worry too much about spin. You'll learn more about that in phys chem and other things, and we won't talk about it too much. The delocalized system must lie in a single plane. This is a good example. This is the benzyl cation, and well, in some ways it's a bad example because that p orbital is actually in the line here, so that the electrons can delocalize through this whole system, and we can draw all of these different resonance structures. This is not the benzyl cation, it's the benzyl radical. That's supposed to be an electron. And we should be able to practice pushing our arrows. So we would have curly fishhooks moving here and then up here. We can move that electron all around this ring system because these things are all in the same plane. Now down here, here's pyridine. And pyridine also, we can draw resonance structures, but we can only draw resonance structures amongst the carbon, the pi system. The lone pair of electrons that are in this nitrogen actually are in what we might consider to be an a p orbital, because our nitrogen is sp2 hybridized. They're in an sp2 orbital that's orthogonal to the pi system. So these electrons cannot be delocalized into this pi system because they're not in the same plane. Here we have a conjugated cyclooctatetrene. It's got 4 double bonds. It is conjugated because we have alternating carbon carbon double bonds with single bonds in between them, but they don't communicate because they're not in the same plane. We'll learn why in the next section when we talk about aromaticity, why in that case that's not a planar molecule like benzene is. The energy of the hybrid is lower than the energy, I should have that in quotes, of any individual contributors. If we think of this as being a primary carbocation, remember primary carbocations are not very stable. So if we could freeze them, which we can't, but if we could, these would be higher in energy. The true structure is going to be lower in energy than we would expect from either of those contributors. So the true resonance form is the lowest energy, and it's because we can combine. The more stable an individual contributor, the greater its contribution to the true structure. So we can see that here, where this contributor is a secondary cation. This contributor is a tertiary cation. If we did calculations, what we would find is that we would have more positive charge density on this carbon than we do on this carbon. So it might not be a half and a half, which we would expect for just a simple allylic radical or cation, but we're going to have more positive charge here. We still have delocalization. It's just that this one is going to contribute a little bit more. Co-commitment with this, equivalent resonance structures make equal contributions to the true hybrid structure. So here we have benzene, and we can draw resonance structures where we just push the pi system around. The true structure has those 6 electrons delocalized over the entire ring. So all the carbon-carbon bonds in benzene are equal length. We know that carbon-carbon double bonds are shorter than carbon-carbon single bonds, and we might expect this to be a skewed hexagonal structure because these bonds should be shorter than these bonds, but because of this resonance, the 4 bonds are equivalent length. We also want to be able to estimate the relative stability of each contribution so we can make some assessment of what the better contributors are. So here's some of the rules for estimating relative stability. Number 1, we maximize the number of atoms with full octets. So even though we have a positive charge on this oxygen, and oxygen's electronegative, and we're used to seeing negative charges on oxygen, but in this resonance structure, all of our carbon atoms, all of our oxygen atoms, but these 2 in particular that are in resonance, have a full octet of electrons on them. In this resonance structure, there's only 6 electrons around this carbon. Okay? Remember, there's a carbon-hydrogen bond there as well. So we get 2 electrons in this carbon-carbon bond, 2 electrons in this carbon-oxygen bond, and we would have 2 electrons in a carbon-hydrogen bond and an empty p orbital. We say that that carbon is electron deficient in terms of the octet rule because we only have 6 electrons near it. In this resonance structure, it has a full octet. So we say that this one would contribute more than this one. So these are kind of in order of priority. This rule supersedes the rules that come underneath it. The next one says negative charge is best supported on more electronegative atoms, positive charges on less electronegative atoms, but then I tell you that 1 supersedes 2. So in this case, we actually have an octet around these 2 carbons in both resonance structures. Okay, so which one? We can't use the first rule in this instance because they both have an octet around the carbons and these carbons. So when we see a negative charge on the oxygen, oxygen is more electronegative than carbon, so the oxygen is better able to support that negative charge. We would say that this contributes more than this. Again, that's because all of them have an octet. Going back to the previous slide, we have a positive charge on the oxygen, and carbon is less electronegative. Carbon should be better able to support a positive charge, but in that structure it doesn't have a full octet of electrons. And here we can see, we can draw resonance structures where here we have positive charge and a negative charge on our oxygen. In this resin structure, we can just push our arrows and end up with this as a resin structure. Notice these are resin structures of acetone. So if we start off with acetone, we can push our electrons like this to get this resin structure. We could also push our electrons. How convenient, we have acetone right here. So notice in these two structures, in this structure, carbon doesn't have a full octet, and in this structure, oxygen doesn't have a full octet, so we can't use that rule to distinguish between these two resonance structures. But in this structure, we have a negative charge on the more electronegative atom and a positive charge on the more electropositive atom, so we would say that this would contribute more than this. Now, you do have to remember that this contributes even more because we have a complete octet around all of our atoms in this resonance structure. So this one would contribute the most to the real structure. This one would contribute considerable amount. This one contributes much less, much less. Finally, this one, the next one, maximize the number of covalent bonds. So in this case, between these two resonance structures, we could push our electrons by moving arrows to each of those carbons where we have a Zwitter ionic structure. This one has more covalent bonds because we have 2 pi bonds, and in this one, the resonance structure anyway, we only have 1 pi bond. So this contributes more than this. What you will find is there's another rule if you go and search for rules of resonance and stability that says minimize the number of formal charges. These two actually turn out to be kind of the same thing. So if we minimize the number of formal charges, we say that this contributes more than this because here we have 2 formal charges and this one has no formal charges. But they're kind of the same rule. You will find some textbooks talk about these as being separate rules, but they really just kind of degenerate to be the same. Is it conjugated? So we can clearly see that this is conjugated because we have alternating carbon-carbon bonds. This one is not conjugated because we have an sp3 hybridized carbon between the 2 pi systems. These ones, as it turns out, these are all conjugated because we have p orbitals in between the pi systems, so that p orbital will line up and can be in the same plane as the pi system. So this is just trying to show you how we can push the arrows to indicate that yes, those all are conjugated systems, and these ones are not conjugated systems because we have these sp3 hybridized carbons in between the pi systems. So now we kind of have a new order of carbon stability. We're inserting in these allylic radicals. A primary allylic radical falls somewhere in between a tertiary and a secondary carbocation. This is arguable. Sometimes we find it is indicated as being a little bit more stable, so they're actually close. And then when this one is looks like a tertiary carbocation, but it has a pi system next to it, so it's going to be more stable. So now we should be able to think about carbon stability a little bit expanded to what we did in the past. There's another way of describing this delocalization, and that is using molecular orbitals. So recall, this is concept from 2513, how we build our pi system for something like ethylene, where we have, here we have 2 p orbitals, and they line up, edge to edge, okay? And we mix those orbitals. We say that these orbitals can mix, and when they mix in phase, they form a more stable molecular orbital, and we can put our 2 new electrons in that more stable orbital. We say we've lowered the energy level because we're able to make molecular orbitals out of these atomic orbitals. They can also mix out of phase, and when you mix them out of phase, we make a higher orbital, but that doesn't contribute to the energy, a higher energy orbital. That doesn't contribute to the energy of the system because we only have 2 electrons in this pi system, and they both end up in the lower energy orbital, and there's no electrons in that orbital up top. So we've stabilized the energy of our system because in the separate p orbitals, each of these orbitals are higher in energy than the molecular orbital. And then once we put our electrons in the molecular orbital, we can think that we've stabilized the system by making these molecular orbitals. Now, one of the rules of making molecular orbitals, you remember, is that the closer 2 orbitals are in energy, the stronger they overlap. What about a carbonyl system? A carbonyl system has a 2p orbital on carbon mixing with a 2p orbital on oxygen. The oxygen electrons are held a little more tightly because there's more protons in the nucleus of an oxygen atom. So it's lower in energy, the oxygen 2p orbital, when there's an electron in it, than the carbon 2p orbital when there's an electron in it. So they can still mix, and what we end up finding is in the molecular orbital, the one where we mix that are in phase, the lower energy one is going to contribute more to what the real molecular orbital looks like. And we indicate that by showing that we have a bigger lobe on the oxygen than on the carbon. This comes from molecular orbital calculations, and that's just the coefficient telling us kind of the relative size of the orbital at those nuclei. So it's a little bit larger on the oxygen than it is on the carbon. Conversely, for the pi star orbital, this is closer in energy to the pi star orbital than the oxygen 2p, so it contributes more to the pi star orbital. When we put our electrons in, we put them in the lowest energy first, and we have a system now that is indicating that we have more electron density near the oxygen, and that makes sense to us because oxygen's more electronegative, and we expect that the electrons are going to be more strongly drawn towards the system with more protons. An oxygen atom has more protons in it than a carbon atom. The next thing we want to see, now notice you'll see these HOMO and LUMO written on everything. So we have 3 things. HOMO just stands for the highest occupied molecular orbital, so it's the orbital that's highest in energy that has electrons in it. As soon as we go past that, we go to the next orbital. There's no electrons in it. We talk about that as being the lowest unoccupied molecular orbital. Sometimes for people that do a lot of radical chemistry, they'll talk about singly occupied molecular orbitals. They often are, I shouldn't say this is also a highest occupied molecular orbital, although it most of the time is. Because it's still occupied, right? It just has 1 occupant as opposed to 2 electrons being in it. So sometimes you'll see when we're talking about radical chemistry, they'll be talking about the SOMO. And that's important to distinguish that orbital from the others, is because when we talk about radical chemistry, it's that unpaired electron that gives the systems their reactivity. So we have a single pi system. What about a conjugated pi system? We can actually think of building a conjugated pi system by now taking each of these orbitals, each of these pi orbitals, and interacting them to build 2 new orbitals. So we can take our orbital that is in phase. We have 2 pi systems, and we can add those constructively, get something lower in energy. We add them destructively. Notice now there's a node. There's a change in phase between this orbital system and this orbital system. That's an area where we have 0 electron density right in the middle there because we have a change in phase. We can also add together these 2 LUMOs. Again, we add them together constructively. Notice now we have 2 nodes in this system, and we can add them together destructively, and we end up with 1, 2, 3 nodes. So as we go up in energy with our pi system, every time we go up a level, we get another node, a region where we have a change in phase between the p orbitals in the system. So in this one we have no nodes in the pi system. There is a node in all p orbitals at the nuclei, okay? So, but we're talking about this plane. And there's no nodes here. The first one, there's a node there. The second one, there's a node here and a node here. And the third one, there's a node between each of the carbons. Now, it's a little bit more difficult to do the mixing when we have bigger and bigger systems, and sometimes when we have an odd number. In actual fact, this is how we do the mixing here. To mix this one, we mix a little bit of this with a little bit of this. And to make this one, we mix these two. And to make this orbital in the middle, we actually mix a little bit of each of these along with a little bit of this one. We can do that mathematically, and you guys don't have to be concerned with that. You're not going to have to get into that level in this course. But the same thing applies. What you will notice is down here with this 3-atom system, we have 3 p orbitals that we're combining. We can combine this in different ways. We could have taken each of the p orbitals and combine them, or we can take combine 2 and combine them with the third one. So there's different ways mathematically to handle this. But notice now here we have 0 nodes, 1 node, and 2 nodes. Notice also in this one, when we have an odd number of carbons in a conjugated system, we'll see these nodes that happen to be right on atoms. As opposed to even numbered system, the nodes aren't right on atoms, they're in between atoms. So for odd number systems, we always end up with nodes, not always, we have some orbitals that have nodes at nuclei. Now, so with our allo system, this is showing 3 electrons. This is an allo radical. This is now the highest occupied molecular orbital, and it's also a singly occupied molecular orbital. This is the lowest unoccupied molecular orbital. In the allyl cation, we only have 2 electrons because we have 3 carbon atoms and we have a positive charge, so that means we've lost an electron. So to go from the allo radical, we just remove an electron, and we're at the allyl cation. And notice now, both of these systems, if we imagine all of our electrons in p orbitals over here, they would all have this same energy level as this p orbital. When we put our electrons in our new system, 2 of the electrons end up in an orbital that's much lower in energy than a p orbital, so we've lowered the energy of our system. For the cation, we've lowered it even more so because we don't have an electron in this thing now that we call a non-bonding orbital. And we'll talk about this bonding versus anti-bonding versus non-bonding in just a second. For an allyl cation, our electrons end up down here. This is our highest occupied molecular orbital, and this is now our lowest unoccupied molecular orbital. We can also have an allyl anion. The only difference between an allyl anion from an allyl cation is if we have a cation, we have a positive charge, we throw an electron in there, what's the charge on our system now? Is it still positively charged? We've thrown a negatively charged electron in it, what is it? Neutral, that's right. But now if we throw another electron in there, it's going to be negatively charged. Okay? So to go from a cation to an anion, you have to give it 2 electrons. To go from a cation to a radical, you have to give it 1 electron. And the same goes true in the other direction. To go from an anion to a cation, you have to pull 2 electrons out. So the allyl anion, we put our electrons in. We now have 4 electrons in our pi system. So this is something I can tell you there will be a question at some point is how many electrons are in this pi system? Okay? So I'll give you some pi system and I'll tell you whether it's a cation or an anion and ask you how many electrons are in that pi system. You'll have to be able to count that. So in this pi system, in the allyl anion, there are 4 electrons. And again, the allyl anion, imagine if we didn't mix those p orbitals, they would all be at this energy level, and we would have 4 electrons at this medium energy level. But because we've mixed and made our molecular orbitals, 2 electrons are in this non-bonding orbital, but 2 electrons are down here lower in energy. So the allyl anion is also more stable than we might otherwise expect. And we can draw resonance structures for the anion as well. And it looks just like the resonance structures for the cation, the anion. The electron density is shared between these two carbon atoms, and it's lower in energy because we've delocalized that charge. What about butadiene? Well, butadiene, notice now we're kind of showing these are each of the p orbitals, and we're combining them constructively, all of them down here. Here's a node, so we have 0 electron density right in between those two carbon atoms. When we go to the next one, we have 2 nodes. Next one, we have 3 nodes. And this just looks like a bunch of p orbitals. So what we're saying now is that because there's a change in sign, they're not mixing. This is a calculation showing what the electron density, a better description, I suppose, of where the electrons are located. Notice that our lowest energy orbital, there's no nodes. There's 1 node, there's 2 nodes, and there's 3 nodes. So a node of 0 electron density occurs in the region where a change in phase occurs between the p orbitals that are mixing. We can continue to extend this. I meant to hide this, but we've already done this. So here we've taken these 3 p orbitals and we've mixed them to form 3 new orbitals. In molecular orbital theory, however many orbitals you start with, you will get that many new orbitals. So if I take 4 orbitals to mix into molecular orbitals, I will end up with 4 molecular orbitals. And this is just showing what they might look like. So here we go. Here's our, we can keep this, and this can go branch out forever. And again, you'll notice that we have down here, these are all what we call bonding orbitals. This is the level of just a simply p orbital that has not been combined with any other orbitals. And one of our set of molecular orbitals may fall in that region. And that's always when we have an odd number of p orbitals in a row. We will have 1 orbital that's non-bonding. Everything that's below that we talk about as being bonding in character because they're lower in energy and we're able to stabilize the system. Whenever we have to put orbitals in these, put electrons in these orbitals, we're destabilizing the system because they're anti-bonding. So these are anti-bonding, bonding, and non-bonding here. So you'll notice in these even-numbered systems, we don't have a non-bonding orbital. Our orbitals are either bonding or non-bonding. So once we have electrons in there, and we'll see that in just a second, and we'll see why what ends up happening is that the HOMO and the LUMOs get closer and closer together. The energy gap gets smaller and smaller as we extend our pi system. We can promote an electron from a lower orbital to a higher orbital by putting energy into the system. Typically, we do this by putting it in the form of light. That light has to have the same energy exactly to match the gap between the lower orbital and the higher energy orbital that you're promoting the electron to. The most common absorption you will see when you put light into a system, typically the lowest energy is what we're going to talk about as being the HOMO-LUMO gap. So an electron can be promoted to a vacant orbital of higher energy by the absorption of energy in the form of light. That light has to exactly match, the energy of the light has to exactly match the energy gap which you're putting that in. Now let's take a look at the electromagnetic spectrum, right? So this is the electromagnetic spectrum. It's very, very broad. You go to the hospital, they use light, electromagnetic radiation of the X-ray region. You don't want that happening a lot because it's not very good for you, but it does have a tendency to penetrate, and you can see things, take pictures of things that are underneath your skin. We can also use UV and visible light. Notice how small the visible spectrum actually is. The visible part of the spectrum, this is expanded. This is what we can see as humans, okay? Cats have a little bit extended. Dogs are colorblind for the most part. Anybody here colorblind? Okay. I bet you, I'm going to bring in pictures. I bet you some of you have some color deficiencies. I do. I'm red deficient. So this is the visible region. Then out here, in terms of energy, this is more energetic electromagnetic radiation than the stuff on the right-hand side. This is longer wavelength, lower energy. So our energy is increasing in this direction, and our wavelength is increasing in this direction. And the wavelength is just the distance between peaks in the wave. So electronic transitions occur typically in the UV visible. They may extend out into the IR and they may go into the UV, but we can promote electrons. In ethylene, the distance between the pi orbital and the pi star orbital is 173. The equivalent, if we had a mole of those photons of that light energy, it would be 173 kcals per mole. It happens to be light of 165 nanometers. We can't see that. Okay? Butadiene, the energy gap is getting, oops, where am I? Okay. Oh, I'm sorry, this is not butadiene, this is hydrogen. Okay, that's why it makes sense. Hydrogen, very large gap, 258 kilocalories per mole. That's just hydrogen gas, H2. That's light of 111 nanometers. That's very high energy light. When we get to butadiene, the gap gets smaller. We get to longer and longer wavelengths. I'm sorry, this is hexatriene. Butadiene, 217 nanometer light will cause that transition. Hexatriene, 250 nanometers of light. We still can't see this, but this is getting closer to the visible spectrum. If we go back, 400 nanometers is blue light. That's when we can start to see it. Violet, actually. And we talk about ultraviolet being higher energy than violet. What about a pi system with a heteroatom like oxygen? So we have our pi system, and then we also have these lone pairs of electrons. As it turns out, those lone pairs of electrons, we often think of them as being in non-bonding, just hybridized orbitals, and they're non-bonding. So we can get transitions at even higher wavelengths, lower energy light, because we're not going from the pi system up here to the pi system up here, but we're promoting one of our electrons in one of those non-bonding orbitals on oxygen into the pi system. As we'll see, although we can do that, we talk about this as being a disallowed or forbidden transition, and that's for symmetry reasons, because this is our pi system all in one plane. It's very easy for light to be absorbed in that extended pi system. Here, this is orthogonal to the pi system, so it is not an allowed transition. And again, in PhysChem, you'll talk more about that. In reality, we kind of lie to you. When we make these little bunny ears on oxygen for carbonyls, we're indicating that those two orbitals are equal in energy. In actual fact, they're not. We really have something that looks more like a p orbital and another orbital that looks like an sp orbital. And the real energy levels of these N systems, we have one, the non-bonding, which would be this one. It actually is higher in energy. The p orbital tends to be a little bit lower, and we talk about that being down here. They're both non-bonding, but they're not equivalent as we always indicate. Same with water. But that's okay. It's nothing to be concerned about. It doesn't affect the way we push arrows and everything. So again, the effect of conjugation, and we can see that here. Take a look at these three even-numbered systems, and we can clearly see as we mix the orbitals, as we extend our conjugation, that HOMO-LUMO gap gets smaller and smaller the further out we extend it. We can detect these things using UV vis spectroscopy. And I just want to, don't worry too much, this is just showing us how we do it. We do it by having a sample, and then we have another blank where we have whatever our solvent is without the sample in it. We send light between the two, and we look at the intensity of those two lights. You're not going to have to know how to do that in this course. But here we see an absorption spectra, and we can have all of these different electronic transitions. This particular compound has a carbonyl group in it, so we have an N-pi star system as well as a pi-pi star absorption spectrum. So that's where we'll begin next class.